going? It's spring.
So the final on Monday or on Wednesday?
It's final on Monday or Wednesday? I think it's Monday. Is it Monday? It's on Canvas, but it should be Monday.
Because Monday, 2:32 Monday.
Yeah, you get 10 minutes in between to recover.
Oh no.
You can take the Wednesday 222 final if you want. You can come to either one. So Wednesday.
I can go to the Monday one?
You can go to the Monday one, yeah.
To go Wednesday, I have facing too.
Yeah.
A lot.
So you get to choose like what kind of overload you want. Yeah, it's kind of crazy.
This class's final is on Monday or Wednesday?
Should be Monday at 12. Check the schedule to make sure.
Yeah, Monday.
And I put it on Canvas.
How about Friday?
Can't do Friday. Friday this week? You want an early exam? How about right now? Surprise final, and we'll squeeze in 50
Can
minutes.
we take it on Monday if we aren't happy?
No.
Okay, well, I'm almost home straight.
Yeah. All right, you ready to play with some state machines?
Always.
Always. All right, so we're not going to do state diagrams. We're just going to look at the behavior of state machines. We're not going to do tables. We're just going to do diagrams and get an idea for the kinds of things we can do with state tables. All right, so here's a state machine. It has two states, S1 and S0. The little asterisk next to S1 means that S1 is the initial state. So when you start the system, it begins in state S1. And you probably remember this from 250. The little arrow with in/out means it's a key. So when you see an arrow with 0/1, it means if your input is 0, your output's going to be 1. So the state machine takes inputs, it generates outputs, and it moves from state to state. And there's a clock that we never actually show on these, and every time the clock ticks, the machine transitions. So depending on what state you're in and what the current input is, you'll go to some next state, which could be the same state you're in, and you'll generate some output. So the first question is, what does this machine do? It obviously takes in ones and zeros. Those are the only input values. But what does it do to the input?
Just a question, is one of the top or bottom arrows supposed to be 1, 1? Because they're both the exact same.
They are both the exact same. Let's make this 1, 0. Thank you.
It goes from one state to the other state no matter what your input is.
Looks like it always goes between one state and the other state. So it just pings back and forth from S1 to S0 back to S1. So that's one key observation.
When it goes from S1 to S0, it just outputs the input, and when it goes from S0 to S1, it's an inverter.
Okay, so when it's in S1 and it gets an input, it just copies that input directly to the output, and it goes to S0. When it's in S0 and it gets an input, it outputs the inverse of that bit value, and then it goes to S1. Also a key observation. So is that enough to describe sort of what the overall behavior is in high-level terms? So what would you say this is doing? So when you're trying to analyze these things, sometimes it's useful just to write a bit string and see what it does to it. Let's suppose this is our input. That's way too many bits for a sunny day. But we start in S1. And we said if you're in S1, you just copy the input to the output. And then you go to S0. And if you're in S0, you copy the inverse of the input to the output. So that'll change to a 0, and we'll end up in S1. So that'll get copied, and we'll end up in S0. This will get inverted, and we'll go to S1. So what's it doing? It's toggling every other bit, starting with bit 2. Well, if this is bit 1, bit 2, starting with the second bit. It toggles the second, the fourth, the sixth, the 8th bit, and so on, forever and ever. Is that useful? I don't know. But that's what it does. Alright, let me give you a little crazier machine. And I would like you to find someone or a couple of people to work with. Just push your desks together or turn around or something and see if you can figure out what this does. It'll take about 4 or 5 minutes and see if you can figure out what this does. So this is going to have 4 states. The initial state is S00, 0. There you go. And let me give you a string if you don't want to come up with your own string. There's a possibly interesting string to play with. So start in S00, and you need to keep track of your state and where you are in the input. Let's see what the output is and see if you can figure out what this is doing. You got the State Machine app on there?
This is the input string. I'm going to put binary numbers and we input this first state, and this is the input. That's what we did.
So what kind of things are you finding?
It's converting them to zero.
It's converting what?
Most of it to zero. There's one exception.
Okay. So half of those transitions should output a 0 and half of them should output a 1.
Because on S01, the only thing you're going to get out is a 0.
I feel like
Correct.
And most things are going to loop there except for if the input's a 0 and it's at S1. Everything else is going to output a 0.
Oh, thanks.
From S11, everything outputs a 1 though.
Yeah, but then it goes to S10 no matter what, and then S10 is either going to output a 1.
Well, S11, if you get a 1, you stay in S11. Alright, you got that.
But which like, are you doing anything close to 0, 0, 1?
So what have you found?
Not a lot.
Is it a shifter? Is it right shifting?
It's doing something like shifting, yeah. What's the output look like for this particular input?
0, 0, 1, 0.
So what is that? Did anybody go beyond this and see what the next output bits were?
The next output's 1.
Yeah, the next output's going to be 1.
And then 0.
And then 0. So this is a 2-bit right shift or a 2-bit delay. Takes your input and 2 clock ticks later it pops out. So everybody remember the traffic light lab from 250? Yay! You built a delay circuit in there,
Yeah.
right? So this is a state machine version of that. You did it with 555 and some latches. But this is the same idea. When a 1 comes in, 2 clock ticks later, that 1 appears on the output. But while it's delaying it, it's also remembering what bits are coming in so that those can come out on subsequent clock ticks as well. But it's a pure state machine, and the way I sort of coded this up, if you look at state ij, j is the latest bit, and I is the prior bit before the latest. So it starts off in state 0, 0. If you get a 1, I'll go to state 0, 1. That 1 is telling me the last bit I saw was a 1. The prior bit was a 0. We're assuming you started off with a bunch of zeros. So if your latest bit was a 1 and the prior bit was a 0, and now you get another 1, I want to go to this state which says the latest bit was a 1, prior bit was a 1. If you get a 0, I'll go here, which is latest bit was a 0, but the prior bit was a 1. And these things just output based on what the prior bit was. If your prior bit was 0, you're going to output a 0, no matter what your current input is. If your prior bit was 1, you're going to output a 1, whatever your prior bit was. Designing this is not like other things we do, right? But the more you design state machines, the more you start to think about things like this, the way you think about algorithms like this, and it eventually becomes very natural to sketch out a diagram to do whatever you want to do. And then your friends start to look at you weird, because what movie do you want to see? And you make a state diagram to answer the question. And but that's okay. Okay, so this is one thing we can do with state machines. We can modify inputs, right? So this is typically what we do in 250. When we talk about state machines, you have inputs and we produce outputs based on those. We can also use state machines to do language recognition. So consider this machine. So S0 is our initial state. And we're not going to produce any outputs here, we're just processing inputs. So I'm just going to have a bit value on my arrows. And I'm going to draw my state as two concentric circles. And when we do a state like this, that's what we call a recognized state. So we can build a machine that takes input and moves from state to state, and when it recognizes the input as matching some pattern, being part of our language, being a valid C program, whatever, it should transition into one of these recognized states. So anytime we're in a state that's represented with these two circles, we can say at that point our input up to there has been recognized by our system. And we can build state machines that recognize parts of a language, or like I said, you can make something that recognizes valid syntax in a program, and so on and so forth. So for this machine, what sorts of strings would this recognize? What are some input strings that would get us to the recognized state? 1, 0. Because a 1 will take us to S1, a 0 will take us to S2. There we go, we're recognized. Anything else?
0.
0.
1.
Boom. 1, 1.
1, 0, 0. 0, 0.
And so on. And once we're recognized, any bits after that, we're still in the recognized state. So is there anything this doesn't recognize?
No.
That's kind of silly. But yeah, I think you're right. So this recognizes all strings. All right, let's make it more interesting.
Does it recognize 1?
No, it does not recognize 1. You're right. So 1 will just take us to here. So it doesn't recognize that 1 string. And it doesn't recognize the empty string. That's a pretty intense language, man. You could like sell classes online to teach people that language. Alright, so here's our initial state, S0. Here's our only recognized state, S1. So 0 brings us here. 0 from S1 brings us back here. A 1 leaves us here, and a 1 leaves us here. So what kinds of strings will this recognize? Definitely a 0.
1, 0.
1, 0. 0, 1.
1, 0, 1. 0, 0, 0.
Will it recognize that? And once you figure that out, you'll probably figure out the whole machine.
it recognizes even-numbered strings that start and end with different digits, and odd-numbered strings that start and end with the same digit.
Interesting. That might be true. I think it's simpler but different from that.
I don't think it's much of a what's all ones. Odd or even.
Just you would get stuff, yeah.
But that's very close. So what do ones do, basically?
Nothing.
They do nothing. They leave us in whatever our current state is. So if we recognize a string, ignoring the ones, it's going to be recognized when we take into account the ones. So if we just look at the zeros, what do the zeros do? Yeah, they just ping pong between the initial state and the recognized state. So if you have a 0, you're recognized. Second 0, you're not. Third 0, you are. Fourth, you're not. Fifth, you are. So any string with an odd number of zeros, this will recognize it. And the ones do nothing. So suppose we wanted to recognize a string containing a 0 followed by any pattern that has an odd number of zeros. But it's got to start with a 0. Say again? Doesn't have to. So I'd be fine with that, because that's a 0 followed by a string with an odd number of zeros.
Could you just add another double?
Yeah, so we can start piecing these together. So let's change our initial state. We'll call it T, and we'll make that our initial state. And we'll say if you have a 0, let's go to our machine that recognizes a string with an odd number of zeros. And if you have a 1, we'll just go to our bad state. And if you have a 0, we will stay in our bad state. And if you have a 1, we'll stay in our bad state. And now any string that starts with something other than a 0, you're just stuck in that state forever. It's never going to recognize it. But if you start with a 0, then it'll do our old, let's recognize an odd number of zeros. So you can start building these things together. And it almost feels like programming. And at some point it is. So this is the kinds of things that Alan Turing and contemporaries were working with in the 20s and 30s. They were studying computation and limits of computation. What can we compute? Are there problems that we can't answer? Are there procedures we can't describe with an algorithm? And these were all kind of sort of nebulous terms: program, algorithm, problem solving, solution. And they wanted a way to study these questions mathematically. And so Alan Turing came up with a model of computation. We call it a Turing machine. And it was a theoretical machine that you could use to execute algorithms, basically, to perform whatever functions you wanted to perform. So let's look at Turing machines. And anything you can do with a modern processor, a Pentium, an ARM processor, whatever, you can do on a Turing machine. Okay, there's nothing extra that you get after 70 years of architectural development that you can't do with a 1920s Turing machine. Now these are faster, and they're cheaper, and they're reliable, and they use less power, and they exist, and Turing machines don't actually exist except like when you make one just because it's cool to make. But the architecture, right, the things we can do with these machines, we could do with a Turing machine. There's a term in computer science, Turing complete. We talk about a computing engine being Turing complete. It means it's as good as a Turing machine. Okay, it's kind of like the gold standard. It means you can do basically anything that we consider we should be able to do. So let's look at this. So Turing machine T, so it's a 4-tuple. Of things S, I, F, and S0. S is a set of states. And this is basically a state machine. I is an alphabet. So it's a collection of symbols. S0 is the initial state. So it's the state with the star next to it, is where the system begins. And F looks really horrifying when we write it mathematically, but I'm going to do it anyway. It's a map from S cross I to S cross I unioned with the set R comma L. But we're not going to worry about this. We're going to draw pictures, and it'll be better. But this is basically your current state and your current input. This is your next state. This is your effectively your output. And this is something we're going to call, we'll just call it movement. Okay, so that's the mathematical version, but let me show you a picture view of this. So we have an infinite piece of tape, and it's sitting on some kind of reel over here. And it comes across, and then it's wound up on another reel over here. And it's magnetic tape, so you can read and write information on it. And so there's this read-write head sitting here. And there's a mechanism that can turn these wheels to move the tape left or right. Okay, so your state table, your set of mappings like this basically see what your current state is, right? So you just have state 0, state 1, whatever. See what your current state is, and see what symbol is currently written on the tape right here under the read-write head. And based on that, you want to do the following. 1, you want to write a new symbol onto this tape. 2, you want to move the tape left or right. And 3, you want to go to a new state. So your state table basically looks like this. Let's say if you're in state 0 and you have the letter A, then I want to write the letter B, and I want to move the tape to the right, and I want to go to state S1. And if you're in state 0 and there's a blank, then I want to write an X, and I want to move to the right, and I want to stay in state S0. And so on. And if you're in state S1 and there's a Q, then I want to write a Q back there, and I want to move the tape left, and I want to go to state 3. And your whole program is just this collection of state transitions. Okay, and you got like hundreds or thousands of these things. But it's just another way of writing a state machine description. Okay, so the tape is infinitely long, which is a nice little feature because it means you have infinite memory. And this movement, we usually, I mean, if you had a tape, the tape would be moving left or right. But when we draw these things out, it's easier to think of this head moving left or right. Right, so we don't have to actually like move the symbols around. We can just draw an arrow for where the read-write head is. So I'll think of this as moving the read-write head. And what the heck can we do with this? Because this is a really weird way to do things, right? So let's look at an example. So this is going to have 6 state transitions, total of 2 states. So if you're in state S0 and there's a 0 under the head, let's go to state S1, let's write a 1, and let's move to the right. So this is current state, this is input, this is next state, this is output, and this is move, the read-write head. Okay, so if you're in S0 and there's a 1, let's go to S1, let's write a 0 and move to the right. If you're in S0 and I'm going to use B for blank. So mostly we're just going to have 0s and 1s, but there could be spots that are blank. So if you're in S0 and it's blank, let's go to S1, write a 0 and move to the right. If you're in S1 and there's a 0, let's go to S2, write a 1 and move left. If you're in S1 and there's a 1, let's stay in S1, write a 0 and move to the right. And if you're in S1 and there's a blank, let's go to S2, write a 0 and move to the left. I don't know what this does. We're going to find out. So another rule is if your state and input don't match any of these conditions, the machine halts. And if you try to transition to a state which doesn't exist, right, it's not going to match any of these conditions, the machine's going to halt. That's how you halt. All right, so imagine your tape looks like this. It's a bunch of blanks followed by 0, 0, 1, 1, and then a bunch of blanks. So it's got 4 bits written, everything else is blank. And suppose we start off and we're looking at this character under the read-write head. And our initial state is S0. All right, so what's the first thing this machine's going to do?
It's gonna write a 1 and move right.
Yeah, so it's in state 0 and there's a 0 under the read-write head. It's going to look for a rule that matches that, and there should at most be one rule that matches. Current state 0, input 0, it happens to be the first rule. So it's going to change to state 1, it's going to write out a 1, so this is going to become a 1, and it's going to move to the right. So now we're in state S1, we've written a 1 down here, and we're looking at a 0.
I'm gonna write again, write a 1 again.
So we're in state 1 and we have a 0. So it's going to write a 1. It's going to move to state S2 and the read-write head's going to go to the left. And then it's going to look for a rule that says if I'm in state 2 and I have a 1 and it's not going to find 1, the machine will halt. So all it did was it took those first 2 zeros and it replaced them with a pair of 1s. Not terribly exciting, but sufficient to do everything we do on computers today. So as with all this stuff, there's analysis and there's synthesis. So let's do some more analysis. And I should have written this down ahead of time because I'm going to have to come up with it on the fly. I'm going to cheat, hold on. Okay. All right, there's 5 rules. So suppose there's blanks on either end. Suppose we're sitting right on top of that 1, and we're going to start in S0. So what is this going to do?
Move us to state 1, right a 1, move left.
Okay, it's going to write a 1, it's going to move left, and we're going to be in state S1.
We're going to stay in S1, right a 1, move left.
Write a 1, move left, stay in S1. Same thing, write a 1, move left, stay in S1. S2, and we're going to move to the right, and there is no S2, so the machine will halt. So it took the string 001 and it changed it into 111. Alright, so what if our input looked like this? 010.
We're starting in S1.
Starting in S0.
Does it put out 101?
I don't know, does it? So we're in state 0, there's a 0. We're going to write a 0. We're going to move left. And we're going to stay in S0. S0 and a 1. We're going to move to S1. We're going to write a 1. And we're going to go left. S1 and a 0. We're going to write a 1. And then we're going to move left. And then it's going to find the blank, move right, and halt. So 010 is going to go to 110.
Oh, I started in S1.
Oh, okay. Let's do one more. 011. So someone in the back. The backish part of the room. So we're starting in S0.
So you're gonna look at the input or the key basically, which is gonna move from S. So which state are we in?
Starting in S0.
S0. So you're gonna stay at S. So you're gonna move to S1. Is it S1?
Mm-hmm.
And then you're gonna do the output 1,
Okay, so that's going to become a 1.
and then you're gonna shift to left.
Okay.
And then you're going to do the same thing again, but this time you're in state S1. So you're going to come down there. You'll just stay on state S1, right 0,
Mm-hmm.
and it moves left again.
Okay.
Yeah, and then you're in state S1, and into line 3, is it?
Mm-hmm.
Yeah, and then you're going to stay next state S1, right 1, and go left again.
Mm-hmm.
Now you're in black.
All right. And that'll take us to S2 and we'll halt. So 011 got changed into 101. So what's the significance of these changes to the input?
Swapping.
You gotta go back to 250 for this. Like second week of 250, I think. What? No.
Two's complement?
It's 2's complement.
Right.
Right? So 0, 1, 1, complement all the bits, add 1, you get your 1, 0, 1. Flashbacks, I can see it.
PTSD more like.
Yeah. So there's a shortcut for doing 2's complement. The shortcut is start from the right and keep all your bits up to and including the first one, and then toggle everything else. So if you've got a number like this, keep the 0, keep the 1, and then toggle all these other bits. If you've got this, keep the 1, toggle the other bits. If you got this, keep the 1, toggle the other bits. And that's exactly what this machine does. Assuming you start off on the right, it says if you got a 0, just keep it and you stay in state 0. So what does state 0 mean? It means we're in the section of our algorithm where we're keeping the bits as they are. We're looking for our first 1. If you're in that state and you see a 1, we're going to go ahead and keep that, but now we change to state S1. And state S1 is the state where we say we want to toggle each bit. So state S1, if you've got a 0, write a 1. If you've got a 1, write a 0. And stay in state S1. And you know you're done when you keep moving to the left and you eventually hit this blank. That's when we can say, okay, go to S2, and we'll halt the machine at that point. Does that make sense? And this only works assuming that you're starting off sitting on top of this rightmost bit. If you started off and you were pointing at, say, that middle bit, you wouldn't be doing the right thing necessarily. Because if that bit to the right is a 1, we should already be in state S1 where we're toggling things, right? So it would be nice if this could somehow figure out where the rightmost bit is.
At a third state where the state it starts at moves right until it finds a blank, and then if it does find a blank, toggle the state to our current S0 and then move left.
Everybody catch that? So we're just going to add a step in the beginning of this. We'll call it I, and this will be our new initial state. So if you've got a 0, let's stay in state I, write a 0, and move to the right. If you're in your initial state and you've got a 1, let's stay in that state, rewrite the 1, and move to the right. But if you're in the initial state and you see a blank, let's move to S0. Let's leave the blank as is, but move left. Now it's going to go boink, 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 boink until it gets to the blank. It's going to back up 1, and then it's going to go to S0 and run our previous program. So you can actually put these things together and write programs. And this is what people did before there were better things to do. Let's see if I can find my favorite state machine simulator. I have it bookmarked somewhere, but of course I don't know where. All right, so let's do a 5-minute break. Let's come back at 1:20, and I will have found my link.